main topic of today is about aging and life estimation of dielectrics. So the first talk of the day will be on aging studies in dielectrics and will be delivered by Dr. Nandini Gupta. So Dr. Nandini Gupta obtained her PhD from IISc Bangalore in 1998. She was a postdoctoral researcher at the University of Windsor, Canada, and the Eindhoven University of Technology, the Netherlands. She has worked as a visiting faculty at the University of Windsor as well as an R&D engineer at EMRC Bangalore. She is currently a professor at the Indian Institute of Technology, Kanpur, India. She works in the areas of dielectrics and insulating materials, partial discharge and treeing, and application of plasma discharge. So welcome, Dr. Nandini Gupta, and please proceed. Ma'am, you are muted.
Thank you, Kingshuk. Let me just share my screen. Good morning, everybody. Today, we are going to almost all day, we are going to talk about aging and degradation of dielectrics. I'll start with the first session. And as usual, my objective is to give you a theoretical viewpoint of aging in dielectrics and how we conduct aging studies in dielectrics to our advantage. Now, when you talk about aging, any equipment, well, of course, we are only going to talk about insulation aging. Any insulation which is in service for a very long period of time will undergo aging. And some of these aging processes we can control, and some of the processes we cannot control. So we will have to look at these things from different viewpoints. So first, let us look at what do we mean by aging of dielectrics? How do dielectrics age? And as usual, my focus will be on polymers because polymers are beginning to be increasingly used in the industry, and also in our lab, we work with polymers. So I will speak from the special viewpoint of polymers in question. We have already discussed certain aspects yesterday when we talked about partial discharges and treeing, because partial discharges and treeing are some of the stress mechanisms which lead to aging of the insulation over a long period of time. But let us look at it from a more broad overview. Now, the first aspect of aging is, of course, the physical aging of any material. Physical aging, the most important effect of physical aging is a reduction in free volume. Now, what is free volume? This is something that we don't really talk about. Essentially, when we're talking about solid dielectrics, there is an equilibrium status of the molecules of the lattice structure such that the material would have a particular volume. And in reality, that does not happen, and free volume is the difference between the specific volume of the actual material and that of the closed packed equilibrium form at the same temperature. So at a particular temperature, we expect a certain close packing of the molecules, which is the equilibrium situation. In practice, that is not achieved, and there would be certain vacancies left. For example, if you look at this figure on the left, here you have one chain, and you can see that every chain leaves one single unoccupied site. This could have been it could have been populated, and if it had been populated, the volume of the material would have been, the specific volume of the material would have been less. But that has not happened, and therefore we have a certain amount of free volume. It makes sense to talk about free volume in the context of dielectrics because many of the insulating materials that we use, for example, epoxy, which we use in the laboratory freely, does have an enormous amount of free volume. And what happens is that as time progresses, with time, this free volume decreases. And the decrease in free volume has the same effect as you would expect. It becomes more constrained, it becomes a more crowded space, and therefore in polymers, remember polymers have very long chains, and our dielectricity is governed by this movement of these chains. As the free volume reduces, the segmental motion of these chains become more constrained. The chains cannot rearrange themselves very easily, and with aging, therefore, the free volume is reduced and segmental motion is reduced. Why do we care about this? Why do we care? Because as I said, the dielectric properties of insulating materials are largely dependent on the motions of this, the arrangements and the motions of these polymeric chains. So if a material has aged, it is possible to dielectrically estimate the age of the material, or the aging, how much the material has aged could be reflected in the dielectric properties. So segmental motions are usually driven dielectrically as well as mechanically. So thermal, temperature, etc. play an important role, but it also affects the dielectric role. So therefore, if you look at the dielectric response of a material over time at a same temperature, the dielectric response will change because the segmental motions of the polymer chains will change, and because the polymeric motions will change because of the reduction in free volume. So this gives us a way of estimating the physical aging of a dielectric. Of course, it can be done mechanically as well, but we are not going to discuss that in this course, in this lecture. So the first thing that I have specified is that physical aging will take place over time. There is no way you can control that, but there is a way of estimating this age through dielectric properties, because physical aging does affect dielectric properties. Are there any other consequences? Of course, the dielectric change, when I talk about dielectric changes due to the segmental motion, I am essentially talking about dielectric spectroscopy, where by looking at the permittivity of the material over time, it should be possible to estimate the age of the material. I will briefly talk about polarization a couple of slides later. Just let me go ahead with this. Sorry. Are there any other consequences? One of the consequences in many polymeric materials, especially thermosetting polymers like epoxy resin, or even semicrystalline polymers like polyethylene, if you have physical aging, you might also expect that there would be mechanical stresses in the material. And a consequence of these mechanical stresses is to increase the microvoid density and size. Munmun, who gave a lecture on, showed you a lab demonstration on partial discharges and partial discharges, is working on electrical treeing, and she has seen that as she continuously thermally ages the material, there are voids which are incepted in a virgin material, and then these voids increase in size. And what do we care? We care because when you have a large number of voids incepting and these voids increase in density and size, other degradation processes begin to happen. For example, in the presence, in fact, I talked about this in yesterday's lecture. In case you have voids, I told you that the electrical trees tend to grow towards the voids. Any voids tend to attract electrical trees and tend to increase the propensity for electrical treeing, and ultimately that can lead to failure. Now, when I talk about mechanical forces giving rise to microvoids densities, where do these mechanical forces come from? Obviously, you can have externally applied mechanical forces, but apart from any externally applied mechanical stresses, because of the working conditions, there would also be a situation where mechanical stresses can be generated internally. For example, if you have slow crystalline processes undergoing in the amorphous region. So for example, epoxy resin has an admixture of a large amount of amorphous region and a large amount of crystalline region. And amorphous regions undergo slow crystallinity. When this slow crystallization of the amorphous region is often called secondary crystallization. When this happens, it will give rise to internal mechanical stresses. So either due to external mechanical stresses or internal mechanical stresses, you can have void inception, and the effect of such aging is to increase the propensity of the polymeric insulation to a large number of degradation processes. It can give rise to electrical tree. It can give rise to partial discharges. And as I told you, partial discharges in themselves lead to degradation process and stress mechanisms in the dielectric. Another thing that we have not talked about is water treeing. Water trees are similar to electrical trees, except that they need humidity or water to be able to grow. And water treeing, in addition to electrical treeing, is one of the important pathways to break down over time. It is not just mechanical stresses or physical aging which can cause the propensity of the initiation of voids. There are other processes also which can produce damaging structural defects like microvoids and micro cracks. And this would be thermal expansion. As I already mentioned, Moon is performing thermal aging studies, and when she thermally ages the epoxy resin samples, she can see the void formation and crack formation. But the point is that even if you do not subject the material to thermal stresses over a long period of time, the simple fact of physical aging will and can lead to increase in microvoid density and size. So this is about physical aging. The next is chemical aging. Chemical aging, as you can figure out, and as we have discussed in the previous lecture yesterday, is where you have modification of the chemical structure of the material. So chemical aging essentially means that the polymer that you start with breaks down into free radicals or free ions. And this happens, so for example, you have X and you have Ra plus B. This polymer R will break, Ra plus B breaks up into segments, radicals Ra and Rb. What are the, so therefore there must be an initiation process which leads to this scission. And this initiative step might be any kind of energy that is injected into the system. Under normal conditions, I'm not talking about any fault situations. I am not talking about any over voltage conditions. I am talking about completely acceptable rated normal or working conditions. The energy that you pump into the system, that gets pumped into the system, could be thermal, could be oxidative, could be caused by UV absorption or ionizing radiation or some kind of mechanical stress. So whenever there is some amount of energy that is available and over time, the polymers break up into free radicals, this is a problem because the free radicals are very reactive. And therefore, what they can do is they can cause further chemical changes in the system. They can cause further chemical reactions in the system. So it can lead to, sometimes it can lead to a good thing in the sense that, for example, if you create epoxy resin, you prepare an epoxy resin sample, and what we do is before we perform any experiments, we just leave it in the laboratory at room temperature in a dry condition, we just leave it. What happens is that just that 21 days aging leads to cross-link formations. The cross-linking is complete, which is what we want. But that may be what we want, but over time, we will have situations that we do not want. We will have chemical changes that we do not want. So chemical reactions are caused. And because many of these chemical reactions are governed by the temperature in the system, therefore, very often, the thermal classification of a material, in the sense that to what temperatures can you use a particular material, decides its thermal class, whether it's class A, class B, class E. That is decided by the thermal temperature, because thermal aging is what drives the chemical aging. And therefore, if you cross the temperature range that is accepted, you will quickly drive it to various kinds of problems. Remember, you would have in a dielectric, even under normal conditions, you would have some leakage currents, and local electric currents are expected to raise the temperature through I²R heating. So you can also imagine that if you have electrical stresses, you do not apply thermal stresses. And when I talk about stresses, I'm talking about normal stresses, not over stresses. If you have temperature, you have a problem. If you have electrical stresses, you still have a problem because electrical stresses drive currents and currents cause temperature rise. Also, oxidative initiation can occur at higher temperatures. So oxidative initiation may occur chemically via polymer processing byproducts. So when you're manufacturing, or for example, when the material is in service, there would be certain byproducts. And these byproducts can cause oxidation of the chemical molecules and the radicals and can cause the material to change considerably. Ionizing radiation, X-rays, gamma rays, high energy electrons, these have energies, very high energies. They have energies as high as 10 to the power 7 electron volts per particle. And therefore, they have the capability that if you place a dielectric in that kind of an environment where they are exposed to various kinds of radiation, it is very natural for the polymers to break up into fragments. So instead of having long chain polymers, you would either have polymer radicals, or even if you do not have reactive radicals formed, you would have small chains that are formed. And once you have small chain, fragmental chains, instead of a long polymer chain, the material will lose most of its, considerably will lose its properties. Also, you might have mechanical initiation of chemical aging, because when you are processing the polymer, you actually cause the polymer to be stressed by various kinds of mechanical stresses, and that can cause bond scission. Presence of water is another problem. I have already talked about water trees. So if you have water present, hydrolysis of the polymer ions can take place, and the hydrogen or the hydroxyl ions that are produced can cause considerable chemical degradation. In fact, when we work with nanodielectrics, we have seen that the presence of hydrolysis and the presence of OH bonds on the nanoparticle surface drives the properties of the nanodielectrics that we prepare, unless we functionalize the nanoparticles and we take care of the hydrogen molecules or the OH ions on the surface. So this is the two broad overviews about aging. Aging can be physical or it can be chemical, and the physical as well as chemical aging, we see that they can be driven by electrical stresses, apart from other mechanical and thermal stresses. So that is the point. We are, of course, mostly interested in electrical aging because all the material that we will be looking at would be stressed electrically, because we are going to talk about dielectrics, and we need dielectrics because we have electrical equipment. So the point is that many of the physical and chemical processes that I talked about will go on even if you do not have any extra stress applied on it. But in the presence of electric fields, the physical and chemical aging processes would be accelerated, especially in case of DC. Electric fields will be responsible for dissociation and transport of ionized and ionizable byproducts. So you start with a material. Apart from the intended material, you will also have some byproducts which are formed during the manufacture or during the process, just like Kingshuk mentioned about dissolved gas byproducts. There will be byproducts. When you apply an electric field, you add extra energy to the system, and then that can cause formation of ions. So neutral molecules will break up into ions, and under the application of the electric field, these ions will be accelerated by the electric field. They will acquire energy from the electric field. So firstly, charged particles will be produced, and these charged particles will be accelerated in the electric field. Once that happens, they contribute to losses. They contributed to losses simply by moving through the particle, simply due to transport through the material. but also because they might be accelerated and they may cause local stress enhancement in a manner similar to what I have discussed yesterday in case of partial discharges. So I will not discuss that. But what I'm trying to say is that when you have electric stresses on a material, there are transport mechanisms, which are dissociation and transport mechanisms already going on, which you will not see, and they are contributing to the degradation, which you will not be able to see. It is happening all the time, just like we are aging all the time, even though we may not signs on the go. Without any visible degradation, the material continues to degrade. That is one aspect. The second aspect is that there can be more severe forms of degradation, and those will definitely be visible. And those are the things that we talk about most of the time. For example, when we see partial discharges happening, we see electrical trees, we see water trees. These are degradation processes which were visible, and they require more severe damage mechanisms. But definitely, we need to study these mechanisms, and we do study aging due to partial discharge, due to treeing, due to water treeing. All this we do study. But we must remember that apart from these visible signs of degradation, there is a continuous degradation which is happening in the material due to physical and chemical aging under normal conditions. The degradation associated with these aging processes are considered low level, and that includes the degradation due to PD and electrical tree. They are called low level degradation. The reason is that all these degradation processes happen at electrical stresses lower than the breakdown strength. So the breakdown strength that would cause the material to actually move towards failure is much higher than the electrical stresses which cause these degradation processes. So these are like incipient degradation processes which seem to be okay, but which are inexorably driving the material towards breakdown, because ultimately that is what will happen. Everything is hunky-dory. You are working as electrical stresses which are well below acceptable values, and at the same time you are actually moving towards a ultimate catastrophic failure. And that is the kind of process that we are interested in today. Now, when you talk about breakdown through degradation, what kind of breakdown are we talking about? Broadly, we can divide the breakdown into two classes. One is mechanically assisted electrical breakdown. When you have compressive stresses in the material tends to contract. As a result, any voids that might be present, it might become smaller in size. Molecular packing may increase. And as I told you, molecular packing is something that we want because that increases the specific density. So if you increase the molecular packing, you have less free volume. So you may be happy with this kind of situation. So yes, sometimes the stresses do things that are desirable, but most of the time that is not the case. So whereas compressive stresses can cause an initial increase in density, so initially it's a good thing to happen, but over time that's not going to continue. And after that, what will happen is compressive stresses will cause breakage of tie bonds and will generate defects. And that's a problem because defects tend to trap charges. Now, what do I mean by trapping of charges? When I have a material which is stressed electrically, there would be injection of charged particles into the material. When there is injection of charged particles, these charged particles move through the material and cause there's mobile conduction, and therefore they cause some kind of losses due to current flow, small current flow. But at the same time, a second thing can happen, which we will be discussing in detail, I think, day after tomorrow, that is trap formation can happen. space charges can accumulate in traps. What are traps? Traps are essentially vacancies, or in the lattice, in the solid lattice, there might be unoccupied states. And when I say unoccupied states, I'm talking about energy levels. There might be unoccupied states, and these can be occupied by some of the charges which are injected into the material. When these material traps charges, the situation that you have is every charge that is resident in the dielectric material will exert an electric field. So over and above the applied electric field, the externally applied electric field, you would have a space charge field which is exerted by the trapped charges. And therefore, the electric stress in the material will increase. So that is what happens when you have compressive stresses leading to chain bond scission and defects are created. Dr. Reddy will be talking about defect formation and damage accumulation in materials this afternoon. So when defects are formed, there would be charges accumulated, and these charges will cause the breakdown strength to be lowered. Essentially, it is not the breakdown strength which is lowered, but because you have a second electric field aiding the applied electric field, you are able to apply lower electric fields before breakdown happen, because within the material, the dielectric breakdown strength is seen by the material much earlier. So this is one situation that you can have where mechanical stresses can lead to electrical breakdown due to formation of defects, accumulation of trap charges, and trap charges exerting their own electric field over and above the applied electric field. Instead of compressive stresses, if you have tensile stresses, it is possible to have crack initiation and growth. If you remember yesterday's lecture, I have talked about mechanical stresses due to partial discharges. And I say the kind of energy that you have in partial discharges are unlikely to actually cause crack initiation. But when you have a material aging over a long period of time, and there is a lot of mechanical tensile stress on the material, what can happen is you can have a considerable amount of mechanical stresses accumulated so that cracks can initiate. When cracks initiate and cracks continue to grow under mechanical stresses, we know what will happen. In those cracks, stream will happen, partial discharges will happen, and the partial discharges will then drive the material to break down over a long period of time. So in these examples that I have shown you, what I mean is there is a mechanical origin of the stress, but the mechanical origin acts in synergy with other processes, and ultimately the breakdown is electrical in nature. Apart from mechanically assisted electrical breakdown, you can also have electrically assisted mechanical breakdown. So electrical and mechanical processes go hand in hand. For example, mechanically, a thermoplastic polymer can yield mechanically when you have, because of the physical pressure exerted on the material by electrostatic forces. So let's say when we talk about breakdown of solids, this is not a process that generally happens in the kind of materials we use in insulation. You have positive charges and negative charges across, let's say, a thin film. And these positive and negative charges attract each other. So there are compressive forces. And these compressive forces can cause the material to grow thinner. And when the material grows thinner under a constant applied field, a constant applied voltage, the electric field increases in the material because V by D decreases, V remaining constant, the electric field increases. When the electric field increases, it can lead to breakdown. We have also seen that instead of before electrical breakdown can happen, the thin film can actually break mechanically. In fact, we have worked with elastomers. Elastomers can be used for energy storage devices. We have worked with elastomers, and we have seen how just by applying electrostatic forces across a thin film of an elastomer, it is possible to make the elastomer completely break down mechanically. It will absolutely tear. Electrofracture is possible. Again, we are talking about space charge, because when you have cracks, in the cracks you have discharges, partial discharges, I told you yesterday, redistributed charges within the channel in which it takes place, or void in which it takes place. So charge can get accumulated inside the void, and these charges can attract or repel each other and can generate electrostatic forces. So when you have electrostatic forces inside a void or a crack, it is possible to have a fracture of the material or a failure of the material through shearing processes, and this is called electrofracture. The presence of cracks in a surface onto which a discharge impinges will also facilitate its eroding effect. So suppose, as I said yesterday, there are situations where we have dielectric materials used in the vicinity where we accept a lot of discharge to happen, or maybe some kind of radiation to happen. Now, if you already have cracks, the electric fields on the surface of this material will be considerably modified, and there would be stress enhancement in small regions. So when you have any discharges impinging on the surface, the cracks will lead to failure. So these are situations where you have electrically assisted mechanical breakdown. Your material can break either mechanically or electrically, but these processes will act in synergy and aid each other and lead to breakdown. So here I have a figure which is taken from Bartnikus's book on, sorry, not Bartnikus, Desado's book on aging. What you see here is we have two clear-cut divisions between two processes. On the left, we have the breakdown processes. And what are the various breakdown processes? Electrical, electromechanical, thermal, and partial discharges. Partial discharges are not instantaneous processes. So you see electrical, thermal, or electromechanical processes will lead to breakdown in seconds or less than seconds. But partial discharges will take a long time for to lead the material, to cause the material to progress to breakdown. So these are the processes which are breakdown mechanisms, and these, when we design a material, we design an insulation, we automatically take this into account that these are the processes which may cause catastrophic failure. So we have to make sure that that do not happen. But what we often forget is there are other processes which we probably cannot interfere with, or we do not attempt enough to interfere with, which can ultimately lead to breakdown, because they will cause degradation over very long periods of time. And when we are looking at power apparatus, we are looking at very large lifetime spans. So it is not enough for me that in case of a laboratory experiment, if we prevent partial discharge, it's okay. But when we are going to design an insulation for practical situation, we have to make sure that these degradation processes can either be controlled or can be estimated, so that we can do a proper life estimation, and it can aid in condition monitoring of the system. So degradation processes are electrical trees, water trees, and various other long-term processes, which, as you can see, takes place over days, months, or even years. So there might be trees incipient in a material which can persist for 20 years before it ultimately leads to breakdown. And these are the processes which are of interest to us in case of aging studies. We need to remember that these processes are generally stochastic phenomena. So when you look at certain defects, when you look at certain operating conditions, you might be able to foretell that this can lead to a problem. But there is no way you can predict that certain spatial homogeneities or certain defects are actually going to lead to a particular lifetime. So therefore, when we are looking at aging studies, why would we look at aging studies? Aging studies are necessary because we need to be able to predict the lifetime of a poly insulation. We need to adopt a stochastic process because there are various homogeneities present, and more importantly, there would be fluctuations on the stresses and the nature in which the material reacts to the various stresses over a long period of time, some of which you can see, some of which you cannot see, and you don't really know the exact pathway that these degradation processes accumulate and lead to breakdown. So therefore, it is very important that we adopt a stochastic process, which means that we must have a considerable number of samples of a given material. We must evolve test procedures so that we can get statistical estimates, and these results have to be statistically analyzed. When I talk about testing a number of samples, how many? So that is in the realm of statistics. We need to look at population samples, how to build population samples, but we also need to remember that in this case, we are looking at destructive degradation, and therefore the ideal situation is not something that we can adapt. We might have to compromise. So, and then once these tests are done, the procedure would be to identify the form of the failure distribution. What do I mean by failure distribution? Asha talked about this briefly in yesterday's lecture, where she talked about breakdown, and she talked about the Weibull distribution and the normal distribution with respect to breakdown. So once we identify which is the failure parameter that we are looking at, so we have to identify the failure parameter, and then we have to be able to fit this failure parameter into a distribution. Once we have decided which distribution we are going to work with, which makes sense to work with, we will have to estimate the shape parameters and the characteristic values. So if you're talking about breakdown, we will look at breakdown fills and time to breakdown, and we will look at the distribution curves of the breakdown fills and time to breakdown. And only after statistical analysis of a sufficient number of samples, we should be in a position to be able to estimate or make any judgments about the material longevity. I'm not going to talk in detail about normal testing. I'm only going to talk about aging tests. But when you undergo testing, there are a certain number of tests which are routinely done. So every unit or every new material may need to undergo a certain tests. Then there are certain tests which are performed only on typical samples, not on the entire population. So all this depends upon what kind of property we are looking at. But when you are looking at development tests, where you are either developing a new design, a new insulation design, or a new insulation system design, or you are looking at a new material which you think will have better properties than the materials which are in vogue, in that case, we have to carry out tests under accelerating conditions. I will discuss in greater detail about what I mean by accelerating conditions. But essentially, the idea is that we will perform the test in such a manner as the time scale of the test program can be within manageable proportions. We cannot take up tests which will take very long time to perform and will kind of render the new design meaningless. But that is one aspect. So we have to perform tests under accelerating conditions, and that is what I'm going to talk about. A second thing is that, as I said, aging is a dynamic mechanism. So even if you perform tests under accelerated conditions, it may be such that in reality, in practice, there might be a number of long-time changes which can occur during service. Operating conditions themselves may change. The material stresses may dynamically change, which may not be possible to simulate even under aging tests. And therefore, such aging parameters will remain outside the realm of aging test, and we have to be aware that even on whatever aging test we perform may not give us the complete information. So a number of long-time changes may occur during service, which alter those factors that determine both the breakdown strength and statistics. I will talk about these factors a little more detail subsequently. But such aging normally takes place too slowly to influence the accelerated test, and hence the in-service of the insulation cannot be fully assessed by this aging test. And in that case, we might have to undertake several other additional investigations. So even the accelerated aging test may not be sufficient. in hand with this accelerated aging test, you might have to see what might have changed. You might have to exercise your engineering judgment, and you may need to take up other in-service tests. So we have been talking about various aging processes. Now, when we talk about aging that takes place in service, all these aging processes will continue. And of this, if you look at the physical and chemical aging will occur. Whether you apply the fields, whether you apply other stresses or not, just by existing physical and chemical, just as a matter of course of time, physical and chemical aging will occur. And therefore, and it will continue very slowly through the entire service lifetime. Therefore, you cannot really prevent these damaging processes. What you can do is probably at the instant of choosing the material, you can think about what kind of environment you're going to put your material in use, and you can accordingly choose the material morphology. Sometimes it may be possible to add chemicals. For example, we sometimes use chemicals in order to retard trees. Tree retardant chemicals are possible. You can use antioxidants. So this kind of things can be done. But yes, you can slow down the process, but you cannot prevent this process. However, we are therefore going to be more interested in the electrical degradation processes, because as I said, electrical degradation processes, electrical fields exacerbate the physical and chemical processes and lead to several conditions which are quite comparatively severe in nature. And these cannot be easily prevented, but again, you can do something kind of through, as Orijit Boshurai mentioned, you can use stress control mechanisms, you can use chemicals in order to slow down, but they cannot be easily prevented. And therefore, if that is the case, you cannot prevent them. You need to have some estimate of how the course of breakdown is progressing. It is therefore an essential part of any test program to determine the generation of such electrical degradation over a period of time and figure out how this will characterize, how this will influence the breakdown characteristics of the insulation. So to the extent that these degradation processes lead to breakdown, we need to understand what is happening. And this is where accelerated aging tests come into the picture. So as I said, my purpose is to undergo at the developmental level, to undergo certain tests under accelerating condition, so that my prime objective is to reduce the time scale of the test program. And this will help me eliminate unnecessary design conservatism. I do not have to have a lot of safety factor. I can sail very close to the margin if I employ scientific methods in the design of my insulation system. So and in doing that, my main tool is, of course, the accelerated aging test. How do the accelerated aging tests work? In this, first, I need to make a model of the insulation system. When I talk about insulation system, I must mention that I am actually distinguishing between insulating material and systems. An insulating system will be composed of more than one insulating material most of the time, and it will also involve conductors. You all know what insulating material means. You have a dielectric, you need an insulating material. So of course you want to choose a dielectric, you decide what dielectric you would like to use, and you characterize that material in terms of its dielectric properties. You measure its breakdown strength, you measure its other non-electrical properties, conductivity, etc. You also measure mechanical properties, etc., etc. So you can characterize the material, and most of the time the manufacturer's data will give you information about the material. But when you put that material in a particular design, the way the entire combination will behave will be very different from the individual behavior of the materials. So, and therefore we have to look at the insulating system in its entirety. An insulating system composed of one or more materials as well as conductors. And many of the aging tests that we perform or are mandated by the IEEE specifications or IEC specifications will actually are aimed at evaluating the individual material behavior. So the individual constituents of a reinsulating system, you have probably already estimated. But when you put them together, the life of the insulation system will be determined by the capabilities of the system as a whole and not as individual constituents. And therefore, material tests alone are not sufficient to determine the expected life of a complete insulation system. So yes, you need to test the material separately, but at the same time, you need to test the system as a whole. To give you an example, which I had also mentioned in yesterday's lecture, say you have a situation where you have air and you have a solid material in close proximity. Or for example, we have worked with functionally graded materials. In functionally graded materials, you have different dielectric constant materials placed side by side. And what will happen is when you apply an electric field across this combination, let's say you have parallel layers of materials with different permittivities. When you apply an electric field across this combination, what you will see is if you just have air and the same electric field, the stress that that air will see is less than the stress that an air gap will see when it is in proximity to a high permittivity solid material. So if you have two layers of different permittivities, the low permittivity layer will see higher stresses because of the presence of the high permittivity layer rather than when it is on its own. So therefore, it is more prone to breakdown in the insulating system than when it is an individual behaving as an individual material. So therefore, as I said, you have to make a model of the insulation system. And when I say you have to make a model, I don't mean that you just take the material and take the system and you just build a miniature model. So you take a power transfer and you build a lab a scale transfer. No, that's not what I mean. What I mean is that you have to decide what are you looking at. What is the physical process that you're looking at? If you're looking at breakdown strength, it is easy. But if you're looking at something else, some other property, are you looking at flashover? Are you looking at tracking? First, you need to identify what is the kind of mechanism, which degradation mechanism are you looking at, and the model that you built to test either in the laboratory, either a computational model or a practical model that you build will depend on which physical process that you're looking at. For example, let's say you are looking at corona happening inside a gas insulated substation, in which case you don't have to build an entire model of the gas insulated substation. You can just take a tank enclosure and you can have a conductor and just a needle plate geometry to simulate the corona. So it depends upon which property you are looking at, which breakdown mechanism or which degradation mechanism you're looking at, and accordingly you build a model of the system. Once you have made a model of the insulation system, you need to subject this model to various levels of higher than normal stresses. And this is where the acceleration comes in. If you expect, and what stresses are we looking at? All kind of stresses that you expect would be, the material would be subject to in the field. You take each of these stresses. So let's say electrical stress that comes naturally. If you are looking at electrical stresses, if you expect that under normal conditions, you expect 30 kV per centimeter, what you will do is, and even if the over voltages that you expect are, let's say 40 kV per centimeter, I'm just, don't pay any attention to the values that I'm talking about. If you're expecting 30 kV per centimeter and you are expecting your insulation to last 30 years, what you do is you go to much higher stress levels, maybe 150 kV per centimeter, and see what is the time to break down in this situation. So you are going to accelerate the deterioration process. Once you accelerate the deterioration process, what is expected is that the failure mechanism will work faster than in normal conditions, and therefore failure will occur in a shorter time than in normal operation. This is not always that straightforward, but I'll come to that point later. So once you have the data over short periods of time, you will have to extrapolate these results from high stresses to normal operating conditions and estimate the service life. So you may be in a situation to be able to say that if a material breaks down in 2 hours at X kV per centimeter, but in normal operating conditions, I only expect 1/10 of X kV per centimeter. So under X by 10 kV per centimeter, it will take me 10 years to break down. I'm just giving you some rough estimate, but it is not as straightforward or at all as linear as I'm making it out to be. And this I will discuss later. So when you are performing the accelerated aging tests, we need to understand that there are a very large number of failure processes that can happen. And here we are not looking at individual stresses. We are looking at the failure mechanisms. Sorry. We are looking at failure processes. When I say failure processes, what do I mean? Say, for example, I talk about, let's say I have a material where I have, let's say the rotor insulation. I have conductors which are in close vicinity and there is an insulation surrounding the conductors, of course. And so this insulation is in close vicinity of conductors. Now the conductors will carry high current or low current depending upon the operating conditions. And as a result, the conductors will increase, the temperature of the conductors will increase or decrease. There will be thermal cycling. And let's say there is an increase in load and therefore the conductors get overheated. When the conductors get overheated, the insulating materials surrounding the conductors will get overheated. Now, insulating materials cannot dissipate heat that fast. Conductors have high thermal coefficients. So high thermal coefficients means the conductors will, sorry, where am I? Yeah, the conductors will increase, will expand, but insulators have low thermal coefficients, therefore they will not expand so much. So what will happen? There will be, so there firstly I have thermal process, I have a thermal stress. As a consequence of this thermal stress, what happens is you have expansion, and as a result of expansion, there is mechanical shear between the material and between the insulation and the conductor. So now you have these thermal stresses leading to mechanical stresses. Because of mechanical stresses, there might be delamination between the insulation and the conductor. Once delamination occurs, there is an air gap formed, or maybe there is abrasion of the insulation. Because of abrasion of the insulation, there might be a gap formation. When you have gap formation and there is electrical field, you know what happens, partial discharges happen. And so therefore you have electrical deterioration. So you start with thermal expansion, then you start with thermal stresses. As a consequence of thermal stresses, you have mechanical stresses. As a consequence of mechanical stresses, you have electrical stresses. So what I mean is this, that you are looking at individual failure processes. And these failure processes, there are many in number, and each of these failure processes is probably driven by one or more stresses. And therefore, the system and its constituent parts, as I keep mentioning, you have to subject the system as well as the materials to the aging test. They will have to be subjected to a large number of accelerated aging tests. So the accelerated aging tests are determined not by a single stress nature, but by the failure mechanism. Many of the accelerated tests developed to model failure, particular failure processes, have been standardized, so we don't really have to worry too much about it, by international organizations like IEC and IEEE. Some of these tests evaluate specific properties like the temperature of a material or the tensile strength or the dielectric breakdown strength, and some of them are designed to evaluate specific properties of the entire insulation system as a whole. So this is about accelerated aging test. I have already mentioned insulated materials. So when I keep talking about various kinds of stresses, I think we are already aware of what these stresses are. These are team stresses: thermal, electrical, ambient, and mechanical. So all these stresses may be applicable. Thermal stresses because of ambient temperature as well as load conditions which cause heating within the insulation system. Because remember, wherever you need insulation only when you have conductors. Wherever you have dielectrics, you have conductors, and wherever you have conductors, you have currents, and therefore you have heat. Electrical stresses because of electrical force, the electric field that is applied, because of trapped charges, because of partial discharge, because of many other factors, electrical stresses will happen. Ambient stresses are of course always there, but it becomes a matter of concern when we are looking at special situations. For example, if you are operating near the seashore or in desert conditions or in high mountains where you have a lot of ice, or you have a lot of, or even in highly industrial pollution, in regions where you have high industrial pollution within the city. So ambient conditions are a problem. Now, and of course, mechanical stresses. Example of mechanical stresses would be, I mean, you have mechanical stresses everywhere, but especially in case of rotating machine, mechanical forces are of importance. For example, when the machine is rotating, the slot liners would be abraded because of the motion of the conductors. So thermal, electrical, ambient, and mechanical stresses, these are the broad divisions of stresses that we need to look at. But remember, ordinarily, we are not just going to look at these stresses individually, but depending upon the effect of these stresses on the particular insulation system, we would have to identify the various, forgive me, yes, we would have to look at what are the most important failure mechanisms and what are the stresses driving those failure mechanisms, and accordingly we would have to perform the accelerated aging tests, and these have been standardized by IEC and IEEE. Then of course, okay, so when we are looking at constant stresses, what we are interested is we apply a constant stress and we note the time to failure, and generally this will be proportional to the number of operating hours. So as long as you keep the machine in operation, this is going to go towards aged. It will drive the aging mechanisms. But apart from constant stresses, you might have transient stresses, which the insulation may be subjected to. For example, due to motor starting, out of synchronization of generators, due to lightning strikes. In this case, it doesn't really matter how long the insulation system is in service. More important is how many of these transients can it be expected to survive. So the number of strikes in that case become important. So we have to dissociate between constant stresses and transient stresses. So the basic principle behind aging test is that you increase one or more stresses above normal levels so that the specific failure process that you're looking at is speeded up. This failure process is something that ordinarily happens in service. You speed up the process by exacerbating one of the stresses. What is the possible outcome of this stress? Now, when you're performing a breakdown test, it is very easy to figure out when the test has passed or when the test has failed. If puncture occurs, it has failed. If no puncture occurs, it has passed. But that is not going to work with aging, because in aging, we are looking at degradation. We are not necessarily looking at catastrophic failure. So once you perform the aging test, what you will get at the end of the day is preferably an equation which predicts the insulation life under operating stress. That means you will be able to do a statistical analysis. I'm sorry. You will be able to perform a statistical analysis of the data that you obtain from the aging test. And based on that, you will also be able to perform some kind of regression analysis, which will allow you to estimate or predict the lifetime of the insulation. Theoretically, this is possible, but this is not what we do, and you will not find any standards which are based on this principle. So the idea is a little less ambitious, in the sense that what you will do is you will work with a candidate system. So let's say you have devised a new material. For example, sometimes we put nanofillers into conventional epoxy resin. And epoxy resin has been in service, and not just in laboratory test, it has been in field, not just in case of accelerated aging, but in normal tests, we have used epoxy resin. It has been tested over real time, and therefore we have a fair idea about what happens in epoxy resin. And this is important because no matter how many tests we do and no matter how many models we build, we will not be able to account for all the things that can happen in service, all the random possibilities. So we take a material which has been proven to be our reference system. And once we have done that, we consider our new material, the nanocomposite, would be our candidate system. And we would perform the same tests on the reference system as reference material or reference system and the candidate material or the candidate system. And we would compare the life of the two. So comparing life measured of a candidate system with a reference material or system tested under the very same conditions, we will be able to figure out whether the proven material would be one that gives, the proven material has to be one that has already given good service life under actual conditions, and our outcome would only be, in case of a new system, would only be a comparison with respect to the proven material or the proven system. So this is the basic principle of aging tests. We must also remember, as I was going to mention earlier, that in case of dielectric breakdown test is easy to figure out what is failure. But with aging, it is not so easy, because it is not necessarily always that we are talking about punctured insulation. So if you are trying to look at a failure mechanism that ultimately over a degradation process is drives to breakdown, fair and good. You know that you will wait. If the material fails, it is if the material breaks down, it has failed. If it does not break down, it is passed. But for other tests, it may be difficult to define failure. For example, even if actual failure does not happen, actual dielectric failure does not happen, the material might be rendered unsuitable for use. And at any point of time, after a certain age, the material is better to be taken out of service, or you would face unexpected outcomes. So therefore, in that case, you would have to look at certain diagnostic tests. For example, if you're looking at thermal aging, what might happen is the dielectric may not break down, but the material becomes brittle. So even if though it does not break down dielectrically, you cannot handle the material because the material crumbles. You do not want your insulation to crumble and just go away. Or the thermal aging, it may lose its mechanical strength. And very often when we use solid dielectric materials, we are not choosing a solid dielectric material just because it is going to provide me a high permittivity or a high dielectric breakdown strength, but it is also put in place to provide mechanical strength. For example, insulation in bushings, we need to provide mechanical strength. So therefore, what we would have to do is we would have to provide some kind of diagnostic test over certain intervals of aging. So there are certain tests which are destructive in nature, and there are certain tests which are non-destructive in nature. When we are looking at destructive tests, we can wait for the material to be destroyed. So the examples of destructive tests are measurement of tensile strength or electrical breakdown. But when we are looking at non-destructive situations, where some specific material property has degraded to the extent that the material becomes unfit for use, in that case, we would have to perform non-destructive tests to estimate the values of the parameter. Examples could be insulation resistance, dissipation factor, partial discharge. If the PD is of very high level, you may realize that it is going to lead to breakdown very quickly, and you might want to take appropriate action before unscheduled breakdown happens. or dissipation factor increasing, maybe it has become very conductive in nature, etc. The methodology for these kinds of failure indicating tests are, you have to first figure out what are the typical values for unaged specimens. And then the specimens will be aged for fixed time intervals. And after every period of aging, diagnostic test has to be applied. This diagnostic test could be an estimation of any parameter, maybe the PD level, maybe the resistance, whatever. And if there is a defined change in the parameter, you will have to figure out what value is acceptable, and when it crosses that acceptable value, it will be considered to have failed, and it will be removed from further aging tests. So the failure indicator has to be determined, and that also requires engineering and scientific judgment to determine what is the failure indicator, and then once this material has crossed that threshold level, it has to be removed from the diagnostic pool. Aging tests are, of course, like any other test, associated with a certain number of errors. And most of these errors come because of the statistical nature of the phenomena, number one. And secondly, no matter how large your population sample size is, it will be limited by very many other factors other than statistics. And therefore, you will always be performing a limited number of tests, and that will result in errors. So the total error can be roughly estimated as a combination of the measurement error. Any diagnostic test will have some measurement error, combination of the measurement error and the statistical error. And various IC recommendations specify the permissible measurement accuracy as 3%. Is my screen visible? Kinshuk, is my screen visible? Okay. So as I have mentioned so far, the analysis of these tests is of crucial importance, and we have to remember that these are statistical processes, and therefore statistical analysis of these tests are important. So let me look at very briefly at the statistical analysis issues that we must be aware of. Now, outcomes of the testings are extremely variable, and therefore the only way to make sense of these outcomes is to take into account, to employ statistical method in order to analyze the results. The objective of my statistical analysis is I need to determine if there are real differences between candidate and reference system. So remember what I say, that even though we talk about life estimation, when we perform accelerated aging tests, what we're really looking at is a comparative analysis between a candidate system and a reference system. And if you perform a large number of statistical tests, you will not be able to exactly replicate the data because of statistical variation. So if you need to differentiate between two data sets, you have to have some parameters which will be able to distinguish or will be able to identify the real differences as opposed to the statistical differences between two systems. Because a normal amount of variation in an outcome is likely, and therefore we will have to employ what are called statistical distributions or probability distributions. Once we use this probability distributions to estimate the data we have, we will have to derive an extrapolation equation based on the aging test at a few stress level to be able to estimate the outcome in a situation at a stress level that we have not performed the tests at. So therefore, there are various types of distributions, and each of these distributions have their typical uses. Now, most of the time in physics or engineering, we use the normal distribution, because normal distribution, you will find that the data that we obtain from very many physical processes nicely fits a normal distribution, and therefore in that situation, that is quite okay. For example, when we are talking about the movement of gas molecules in a heated or unheated condition before breakdown, that can be very nicely defined or described using a normal distribution. But then we have log normal distribution. Log normal distributions are generally used for gaseous diffusion or chemical reaction rates. What we are interested in dielectrics are Weibull distributions, because Weibull distributions are the distributions to which the life data or failure data are best approximates. Particle size distributions, so any kind of Wickling phenomena. Because, for example, when you're talking about breakdown, it does not matter what is the average property, variation of the property, the average property. We are not interested in the average property. We are interested in that one property, which is the weakest link. So if this material has one weak link at one particular position, even if elsewhere, on an average, the material is very good, the weak link is what we are interested in. So whenever we are looking at weak link phenomena or extreme value statistics, it is the Weibull distribution that best describes the distribution that we would have. Extreme value statistics are also there. Logarithmic extreme value statistics are also there, which have their own uses. We are not going to discuss them. We will stick to normal distributions and Weibull distributions. Now, this is the normal distribution is something that you're all familiar with. X is your random variable. If you're doing a breakdown test, as Asha pointed out yesterday, then X is your breakdown strength. So you build a probability distribution, which somewhat looks like this. And so you have on the x-axis the random variable and the probability on the y-axis. And what you estimate is the mean value of x as well as the standard deviation of x, the standard deviation. So mean value is the mean value, of course. And because it is a statistical distribution, there will be a spread of the data around the mean value, and estimate of that spread is the standard deviation. So how much will the data that you have individual data vary from the expected mean value? So the mean value is your expected value, and the standard deviation gives you the spread of the data. Now, if you look at this particular graph on the left-hand side, you have three normal distributions with varying mean. And for example, if you were looking at if X were to be breakdown strength, naturally you would choose the material which has mu equal to 1, because obviously it has the highest breakdown strength. On all other shape of the curve, the shape of all three curves are the same, so the decision can be based completely on the mean value. But if you look at the curve on the right-hand side, you see that the mean value of all these three distributions, all these three are normal distribution, and the mean value for all these three distributions are the same. But the standard deviation is different. For a smaller value of standard deviation, you have a peaked data, and as the standard deviation increases, you have a distribution which kind of spreads. You have a higher spread, which means that the data is likelier to deviate from its mean value. So in this case, which is the data that which is the material? If these three data sets correspond to three different materials, which is the material that you would choose? Obviously, the material that you would choose is the one with the smallest standard deviation, because even though, let's say they all have the same breakdown strength, in case of the material with sigma equal to 0.5, you have more you have more reason to rely on that data, because in this material, most of the breakdown will happen near about that particular value. Whereas in the material with standard deviation sigma equal to 2, you would have many breakdowns at values far away, much higher or much lower than your mean value, which is not this unpredictability is not something that is desirable in engineering. Another thing is that you will find that most normal distributions, you can decide what is the confidence interval. You can, let us take this example case. We find that 95.5% of all data is expected to lie in plus minus 3 sigma, which means that suppose this is a data pertaining to the thickness of an insulator, and you're making this insulator and you're expecting the insulator to have a thickness of 3 millimeter, and that is what is your desired objective. And let's say it has a standard deviation of 0.1. Then you will find that 95.5% of all such parts made are expected to have a thickness in the range of 2.8 to 3.2. So that is the deviation that you expect. So if you have decided that, yes, I want a material with thickness 3 mm, but if it is 2.8, it's okay. If it is 3.2, it is okay. But beyond this range, it is not okay. Then you will have an acceptability of 95.5%, and the reject or scrap rate is expected to be 4.5%. Of course, these are all expectations. In a particular sample, you might have variation. Now, that is about the probability density function. But when we are talking about breakdown data, we don't work with probability distribution functions. We rather work with cumulative density function. And the reason is this, that, okay, first of all, what is the cumulative density function? The cumulative density function at a value V tells me what is the total probability of failure at voltages of V and below V. Now, when I apply a certain voltage across a material, I'm not really interested. See, air, if I apply a 30 kV per centimeter across 1 centimeter thickness of air, I'm not really interested in whether breakdown occurs at 30 kV or 20 kV or 15 kV. Or 35 kV. What I am interested in is what is the probability that if I continue to apply 30 kV per centimeter, it will be withstood. So I am interested in the withstand probability of that voltage, which means any value below that. So up to 30 kV, I can exert on the material without any consequences. That is the outcome that I'm interested in. So I am interested in all the probabilities that are at that particular voltage and below that particular voltage. So basically, I'm interested in the area of the curve under a particular value. And the cumulative distribution function gives me exactly that. So when I should take this value, breakdown voltage V50, it means that at that particular voltage, the cumulative probability of failure at V50 or any value lower than V50 is given by 50%. And that is what I am interested in. So depending upon, for example, when we perform insulation coordination, when we are looking at the probability of overvoltages, we use a probability distribution function. But when we are looking at the probability of the insulation failure, we are looking at the cumulative density function. So depending upon what is the physical significance of the random variable, we will have to choose whether we are going to look at the probability distribution function or we are going to look at the cumulative density function. Sometimes instead of using normal distribution, we use log normal distribution. For example, for aging data, we do use log normal distribution because not all the time we are looking at breakdown characteristics. In fact, whenever we are looking at any property, aging property, which is governed by the Arrhenius reaction rate, we can approximate the data or study the data, fitting it to a log normal distribution. The log normal distribution is nothing but a normal distribution where the random variable, instead of taking the value of the random variable, we take the logarithmic of the value of the random variable. But in case of breakdown strength, we actually look at Weibull distribution. This is widely used for voltage endurance test data and for breakdown voltage measurement. This is an extreme value distribution. Actually, Weibull distribution, you can have 2-parameter Weibull distribution and we can have 3-parameter Weibull distribution function. In our case, we don't need to bother about the third parameter, so we stick to a 2-value Weibull distribution, which is given by fx equal to, which is given by fx equal to 1 minus e to the power minus t by alpha to the power beta. Alpha and beta are the parameters of the Weibull distribution. Alpha corresponds to, is analogous to the mean value of a normal distribution. So it gives me the value, the expected outcome of the, or expected value of the parameter. So it's the expected breakdown strength if you're talking about breakdown strength. And beta is analogous to the standard deviation. So beta gives me the spread of the data. So I have examples here of two Weibull distributions. In the first case, in the left-hand side, you have two distributions, both of which have the same spread, beta equal to 6, and alpha is the value that is different for these two distributions. In one case, alpha is equal to 2.5 and alpha is equal to 5.3. As you can see, the x-axis is a time to failure or the breakdown strength. So obviously you would choose the material with a higher value of alpha because that material, the second material, will be able to withstand higher dielectric stresses. Ordinarily, the value of alpha is chosen to be that value which has 63.2% probability of occurrence. It's not visible. Now? Okay. Sorry about that. I didn't realize. So as I was mentioning, maybe I will repeat what I was saying. I'm talking about Weibull distribution, two parameter Weibull distribution with alpha and beta as a scale parameter and the shape parameter. Alpha is the scale parameter. It is analogous to mean value. So if you look at beta is the shape parameter, which decides the shape of the distribution, and it is analogous to the standard deviation of a normal distribution. So if you look at the figure I have on the left, we have two materials. Both of them have the same shape parameter, beta equal to 6. In one case, alpha is 2.5. In the other case, alpha is equal to 5.3. If you look at the x-axis, the random variable is either time to failure or the breakdown stress, and therefore it is completely obvious that we will choose the material with the higher value of alpha equal to 5.3 because this material is going to be able to withstand greater stresses. And the other thing that I mentioned, if you look at this line that I draw through the two data, in determining the value of alpha, we choose the data, we choose that value of x, which has 63.2% probability of occurrence. So that is what we have chosen here. If on the other hand, if you look at the data on the right-hand side, again, I have two materials and they both have the same value of alpha. So 63.2% probability. The other values, the other probability values are different, but the 63.2% probability value for both material is the same, and that is equal to alpha equal to 4. So therefore, the breakdown strength or the time to failure that I expect to happen with 63.2% probability is the same for both materials. So one would imagine that there is no reason to choose either one of them, but there is, because if you look at their beta values, the beta values are different. In one case, beta is equal to 3. In the other case, beta is equal to 6. A higher value of beta means that your distribution is more picked, and therefore you are more likely to have an outcome which deviates from the 63.2% value. And therefore, you will choose the second material again in this case, because this has a beta of 6 and alpha equal to 4, whereas this has a much lower value of beta, and therefore it has a larger probability of your random variable deviating from the expected value of value with 63.2% of occurrence. So this is about distributions. Now let me quickly talk about life prediction techniques. I don't have a lot of time. Okay, so you use these distributions to compare between materials or material systems. I'm not going to go into specific examples or applications, but this is the theory behind how you decide whether a reference system is, whether a candidate system is better than a reference system or not, depending upon the diagnostic failure indicator that you use. Now, let me briefly touch upon the life prediction technique, because even though these are not used in standards, it would be nice while designing a system to be able to predict the life that we expect. In life prediction, we have two broad models that are used. The first is the Arrhenius model. I've already touched upon this. Whenever you're looking at any kind of aging system, which depends upon chemical reactions, because the rate of a chemical reaction depends on the activation energy of the material involved and the absolute temperature. So this is a model which is dependent on the activation energy as well as the temperature. And any aging process which can be expected either to depend on chemical changes or for whatever physical reason or engineering reason, you can approximate that it behaves in the manner of chemical reactions can be governed by the Arrhenius model for aging. But you should remember that the Arrhenius model assumes a single chemical reaction. So therefore, there will be some approximation there. This Arrhenius model for aging, which is based on the Arrhenius chemical reaction rate, states that the rate of insulation aging approximately doubles for every 10 degrees Celsius rise in temperature. So this is something that you would use for thermal aging conditions. It is given by ln T equal to delta H by KT plus B, where T is the insulation life. So you're predicting the logarithm of the insulation life. Delta H is the activation energy and B is a constant depending upon the material. Model. So an example would be how would you set about using this model in your aging test? You would first have to decide on the number of samples you would choose, and you would take a large number of sets. Well, not large number, several sets. And for each set, you would have to take a large number of specimens. So maybe you would take each set consisting of at least 3 specimens. I say at least, the more the number of specimens, more reliable is your data, but at least 3 specimens have to be there. Each set is then aged at a different temperature. And these temperatures have to be in excess of the insulation's normal operating temperature, because we are doing accelerated aging test. Aging is continued on each set of specimen until a desired endpoint is reached. This desired endpoint, as I say, depends upon what property you're looking at. Are you looking at breakdown to happen, or are you just looking at the conductivity to go beyond a certain value so that the material cannot be considered to be a good insulator anymore? Something of that sort. So the failure indicator is something that you have to decide, and I have already discussed. The property of the insulation and the value of that property, which you will consider to be a failure point, will have to be carefully selected so that it has some meaningful correlation with the product in service. You cannot set a high parameter when you know that in service you're not going to be able to replace when the brittleness reaches that point or the conductivity reaches that point. So that is where your engineering judgment comes into the picture. Once you have the data, you will plot the log normal median life for each set. The best fit line to the median points is then found. You can use some statistical technique to fit a best fit line to the data. So these are the median values for every set. So you have 1, 2, 3, 4 sets. Take the median values for every set, and through the median values of every set, you obtain the best fit line. And this best fit line can then be extrapolated to derive an estimate of the expected life of the insulation under normal operating temperature. So you might be performing at 300, you may be performing beyond 300, but you will probably be estimated at 140. Now here there is a very important thing to be mentioned. Let's say you're performing at 250. When you expect to operate at 150, you have to make sure that all the chemical processes and the physical processes that happen at 250 are the ones that happen at 150. Say, for example, you have a material which melts at 250. You will not even be able to test, and it will make no sense to test at 250. Maybe it's a material which undergoes certain chemical process. Maybe it's a material which has certain chemicals which will react beyond 220. But you are expecting to use it at 120. There is no point in operating at 220. So when you choose the aging test and you accelerate the aging test, you need to remember that you have the same conditions as in the field, which means the same failure processes must be there and no additional processes must come into the picture. So for example, if you're performing electrical aging test, you do not want, so we know that when we cross, we will discuss this in one of the sessions, we know that when space charge accumulates in a material, now beyond a certain field, only space charge accumulates and then electrical aging occurs. So if you work below that threshold field for space charge accumulation, you're not going to have any aging due to space charge accumulation. So therefore, you cannot use those different fields for the accelerated aging test. So it is very, very important to be able to choose the failure indicator as well as the operating accelerated test values at meaningful values, keeping the physics in mind. Apart from the Arrhenius model, we also have the inverse power model. We have the inverse power model, which is most often used to estimate the in-service life of electrical insulation, where we have the ratio of the testing time and the service time given as an inverse power law of Vs by Vt, where Tt is the testing time, Vt is the testing voltage, and Ts is the service time, and Vs is the service life. So often this exponent, which will have to be obtained using the data, it is often assumed to have a value of 7. So in the same manner as the previous test, you have to decide a large number of sets. You have to take several sets of specimens, and each set will have several specimens. Each of the several sets of specimens have to be subjected to a different elevated voltage level. It has to be higher than the normal voltage level in service. And for each case, you have to measure the time to failure of each specimen. And in this case, we do not use log normal data. We use Weibull characteristics for each of the time to failure data for each set. And then these characteristics times to failure are plotted versus the voltage stress. Generally, if you fit a proper inverse power model, you will be able to obtain a straight line. So a best fit is obtained, so you can vary the exponents and you can obtain the best fit line for each of these exponents. The best fit line is then projected through the characteristic times to failure by least square means, and this will give you the voltage life curve for the dielectric understudy. And using this, you can estimate the lifespan of the insulation understudy. The slope of the line is numerically equal to the negative reciprocal of the life exponent n. Generally, n can vary widely. I say that often the value 7 is taken, but it has known to be, it has been known that people have taken values as low as 3 or as high as 30. The value of n will depend upon the material, it will depend upon the insulation system, it will depend upon many other factors, many other operating conditions. So it is very difficult to predict beforehand what value you can choose, but the value of n can vary significantly. Once you have determined the value of n and obtained the best fit data, what you can do is you can extrapolate. So for example, you have data which gives you time to failure in seconds or in hours, and with that you can extrapolate data for failure in the range of years or months. But again, as I said, the failure mechanism should be the same. As you keep on increasing your voltage level, for example, you should not, for the accident, I already mentioned the case of thresholds filled with charge accumulation. Then, for example, partial discharges. It might be that at a very high level, certain partial discharges or certain corona, which will not happen under operating conditions, begin to happen. So it is very important to remember that the failure mechanism is true to the service conditions. So values for Weibull distribution parameter for a given dielectric and a given set of operating conditions will remain constant throughout the service life of the dielectric. And from here, from this expression, you can obtain the life of the insulation. It depends upon the voltage, service voltage, service test voltage, service time, test time. It also depends upon the volume of the dielectric and service and the volume of the test under test. Obviously, the volume under test is going to be much less than the volume under service, and you have to scale accordingly. To give you an intuitive feel why the volume matters, if you have a large amount of insulation volume, it is likely to have the probability of having damage mechanisms, to have defects, the possibility of having voids, probability of having traps, trap levels are much higher. So higher the volume of insulation, more likely is failure. And therefore, this is important that we need to scale the outcome of the regression analysis. We have to scale that with the ratio of the volumes of insulation under test and in service. So this is about all. And these are the references that I have used for my lecture. Thank you, everyone.
Thank you, ma'am. We will now have the questions. If you have any question, please raise your hand. There is one. Okay. Ma'am, can you please make me co-host so that I can unmute?
Sorry. Wait. Yeah, I've done that.
So if there is any question, please either raise your hand or type it in the question and answer. We have one question from Niharika Barua. Is the 63.2% value in viable distribution decided empirically?
Yes, it comes from, you mean the 63.2 value? I mean, why we choose 63.2? Is that what you're asking? Or, I mean, why we choose not 50% and 63.2%? Is that what you're asking? If that is what you're asking, it comes from the statistics, yes. From the statistical, I don't exactly know why it is 63.2%, but it is a statistical parameter. So just like normal values are characterized by 50%, viable distributions are characterized by 63.2%. I don't exactly know the reason, the mathematical reason. Okay,
we have one more question. Satyajit Panigrahi has asked how to conduct this material degradation test, namely FTIR, SEM, etc., on full in-service insulators rather on test samples.
You cannot.
Any more questions?
Okay, then I think we can break.
Okay, we will have one announcement here that.
Go ahead, Kinshuk.
Yeah. So, with the conclusion of this lecture, we have an announcement that we are extremely glad to announce that we have the opportunity to have a special session on dielectric polarization and other practical issues on dielectric by the eminent professor, Dr. Gorud Govindu Raju. Most of you must have heard of Professor Raju from his famous book named Dielectrics in Electric Field. He is former head of the department and an emeritus professor at the University of Windsor, Canada, and a fellow of the Institute of Engineers. We will have a session from 5 p.m. tomorrow after the conclusion of the regular sessions. And also you will be informed via email about the schedule and joining link for this talk. Thank you.
So we will reconvene 2 minutes later, or when will we reconvene?
12:30.
Yeah, we will have our second talk of the day from 12:30 on assessment of material degradation using physiochemical methods by Dr. Alok Ranjan Verma.
Yes, so just to add on the question which was asked, the last question regarding this FTIR and SEM. So am I audible?
Yes, you are.
Yeah.
That
answer. There are some more questions.
Yeah. There have been other questions.
Yeah, please, Alok, go ahead.
So probably I'll answer that question in our discussion, or you may get the answer while I'll be covering some of the methods of these methods of FTIRs and other techniques to, analyze the material properties. So in that case, you'll be getting this answer. So just to add on that.
Okay, sir.
You will talk about these kind of assessment techniques, FTIR, etc. So maybe you can clarify any other questions you might have regarding that during his session.
Okay, Ritanjali Behra has asked, in Weibull distribution, can we select alpha and beta values randomly?
You do not select, you obtain it.
Yeah.
It has to be, so what you have to do is you have to take your data and the data that you obtain from your experiments, and you have to fit it to your probability distribution. So once you obtain the distribution, you will analyze the data and you will fit it to the Weibull distribution curve that I had given you the formula for. And from that fit, you will be able to obtain alpha and beta. Of course, there are statistical tools already available which will do it for you without you understanding, but it is always good to understand what you're doing. So just as you have a formula for obtaining mu and standard deviation for more normal data, you also have formula to obtain alpha and beta. So they are not obtained randomly, they are obtained from the data distribution.
Okay, we have another question.
Experiments.
We have one more question. Nilesh Lokhande has asked, many times we faced issues on material like epoxy degradation due to moisture or sometimes humidity issues which create failure on insulation level.
Right, that is expected. What is the question?
Yeah, I also didn't get what is the question. I might, okay, I will unmute him. Yeah, Nilesh, you can ask what is your question actually.
Hello.
Yes, Nilesh.
Audible.
Yes.
Many times during service condition, due to some moistures and humidity condition on the insulating surfaces, so that sludge occurs, and what it creates when the feeding during the live installation going on, some cracking noise and other things occurred. But when we sometimes we clean the external surface, and then we took some major value and other things, but it functions very well. But after some longer prolonged period, maybe 15 days or 1 month or 1 month of time, then again customer complaints occurred that these are the issues relevant to the humidity and other things. But every time it is not possible, so we many times apply some lacquers and other things, so the moistures cannot penetrate inside the surfaces. But I just want to know how is there any calculations in terms of this?
So what you would probably need to do is, what you're talking about is ambient stresses. This is what comes under, remember TEM, it comes under ambient stresses. So normally if I was working in the laboratory, what I would do is I would, in fact, that is what is done in standards also. You would have to simulate that particular pollutant or contaminants that you have on the surface. You would simulate that in the sense that you would find out the composition of whether it's just water or whether it's something else because of the water attracting something else. You would perform the experiments in the laboratory and do exactly what I said. You would perform aging tests to estimate how quickly that leads to failure, or whatever failure mechanisms you are talking about, which causes the customer to complain. And then if there are two options, this can give you an estimate about how frequently you need to maintain, in the sense that you can remove or clean the insulator. That can be, you have to do this periodically. You don't have to wait for the failure to happen. That is one option. The other option is, as you said, look at a different candidate system where you have lacquers or you have insulating coatings, and perform the same test with those coatings and see if that improvement is worthy of your design change. I hope that answers the question.
And sometimes this means we already conducted some many iterations, but we are not able to goes on means conclusion phase, because some oil industries or some carbon cellulose content. So in some carbon cellulose, due to some black surface of that the cellulose, which again create a different environment. So many times in when we conduct this kind of the test in our laboratory, or some standards relevant to the IEC, so when we go for that aging test, but
what you
these contaminants we are not able to means under that specified specify a requirement. So that sometimes those are the issues. So how we can resolve those particular requirements in aging test?
If I understand what you're saying is that when you look at the standards, the contaminants that are specified by the standard do not correspond to the real situation.
Yeah, yes.
That is one issue. You might be also
Mhm.
talking of a second issue where you do not know the nature of the contaminants. I do not know if that is all. So yes, that is where the randomness comes into the picture, in which case I would imagine that in the second case, in the first case, if the standards do not specify, you will have to decide for yourself what are the contaminants, non-standard contaminants that you are coming across, and you will have to perform your own test with that situation. But if you say that you do not even know the composition of the contaminants, there is only one way that you can go in case of such random situations: collect a large number of filled samples and perform tests from them.
Okay.
We have another question from Satyajit. Satyajit, you can ask the question. I have unmuted you.
Satyajit's question I've already, oh no, it's a new question.
Yeah.
Ma'am, am I audible?
Yes, you are.
Yes.
Ma'am, my question is, where we are doing this material degradations and on the test samples, we are considering a small in geometry in length and breadth. But when we are doing in the full insulator, then it is of means distributive kind of thing, means the all sets and all other things are there. So with the proper, what are the effect we are seeing in the small sample by doing the only material?
I get your
The same thing
question.
can be expected from the.
I
That
get
is the
you.
question. It is dependent on the shape of the insulator, how we are designing it, because in porcelain the shapes are different. In composite also we are having same other sets and other creepage distance. So that kind of properties are also affecting the stresses or not.
Yes, that's the point I was trying to make. This is very pertinent and this is very important. Firstly, as I said, it is not the material property which is important. It is the insulation system as a whole important. So when I say insulation system, it takes into account the fact that if you have a different shape, if you have a different geometry, if you have a different assembly, things will be different. And this is where, the point of the model is important. When you make a model, you're not trying to just take the material, or even you're not going to just take a scaled down model of the actual system. You have to figure out what is the failure process you're looking at. So when you say, let's say you are talking about the shape of the electrode, as soon as the shape of the electrode changes, let's say you go from a uniform field to a non-uniform field. When you're looking for a uniform field, you're modeling a uniform field breakdown. But if you are looking at a non-uniform field, you may be looking at partial discharge or corona. So you have to identify which is the failure mechanism that is of importance in your service assembly, and then you will have to have a model which replicates that failure mechanism. For that, you will probably have to replicate not only the shape and size, but you may also have to change other assembly parameters, because in a scale down model, you may not be able to, just by scaling down the dimensions, you may not be able to replicate the failure mechanism. So it is very easy to talk about, you have to do this, but you have to do that. But if you do not have a standard, then it is very difficult. I mean, you will have to spend quite a bit of time to figure out how to build your model. It's not trivial. All of the things that you mentioned do matter. Yes.
Okay, it seems we don't have any more questions. So we will end this session and we will begin at 12:30. Thanks, ma'am. Okay.